Okay, so this is Stewart 15.1, or just the introduction to double integrals, Fubini's theorem, and the derivation of double integrals. So double integrals just look like this. And instead of being for one variables functions, it's now multivariable or two variable function. So function of x and y, and it's over the with respect to the area. So it looks like this. Right, so z is equal to f of x, y. That's just the function's like value, but you can interpret its height in this case. So if we draw something like this, a surface that looks like this, is just going to be a 2D surface that is a multivariable function or a two-variable function, which we can find the volume under, and that's what a double integral is basically looking for, the volume. Okay, so with how in one variable functions, we can divide it into slices along like the x, for example, or the y, but usually it's the x. So like we have this. You can take like a small slice of dx, and if you add up all the small slices through a Riemann sum, you get the total area underneath, or at least like a really good estimate to it. We do the same thing here, except now we take slices along dx and dy. So let's say that x goes from a to b, y goes from c to d. That means that like here, for example, could be the start point of the x. Here's the end point. Here's the start point of the y. Here's the end point of the y. It's just kind of like expanding it to now be 2D. And so, yeah, let's write that out. So x exists between like a, b, y exists between c, d. And we're basically saying we want to find, or what we're trying to do is find the double integral, right? But that's just going to be interpreted as the volume under. And so to do that, we need to take slices again. So let's like pretend there's a little box here, like on the surface, or at least it has one tangent point on the surface. And let's say that box, yeah, it has like some x star, y star. Then the value of f at this x star, y star is the average value of this box's this box through the function, right? So we can say f of x star, y star basically tells us the average height of this little box, or the average volume of this box here. Or it doesn't tell us volume yet, because we still need to incorporate the width and the length for the volume, right? So yeah, let's do that. So we're doing it this way. So I'm going to draw this like here more neatly. Okay, so this way is delta x, this way is delta y. Just imagine it's the same box, right? We have our delta y, we have our delta x, and we have our height, or our value basically, when we put it through f. So this volume here of this little box is just delta x, delta y, times f of x star, y star. So this is a volume of 1. We have like however many we have here, right? This is like a whole surface. This is just one box. So we have to add up all the boxes like along this way, all the boxes. So all the boxes along our x direction, or y direction, all the boxes along our x direction. Right, so we're basically dividing the surface into a bunch of tiny boxes for us to add up. Okay, so we can put this back into their potential Riemann sum, right? And we're saying the sum, let's say we can split this x from a to b into, let's say, m sections, right? So we're splitting this way into m sections, and we're starting at 1, and we just want to add up all of the boxes this way, or all the values of the boxes this way, and we also want to add up all the values of the boxes these ways. So this we can call, we're dividing this way from C to D, we can divide it into n places. Okay, so n, and yeah, we're just adding this entire volume. So each box we're adding up. And this should give us the total volume, or at least like an estimate to it, right? So now let's say we let m and n grow to infinity. Or basically we make the grid finer and finer, right? So there's more and more lines through each way, so that we can basically say each little box, eventually this grid gets so fine that it's basically just the entire surface, right? And also this way, but we're basically saying each of these boxes gets so small, it's basically just a point. Okay, so it's like, that's our little box here. So we could drop this little special x star, y star now, because there's only going to be one point in the box anyways. And this double integral becomes, or double Riemann sum becomes our double integral, right? So say limit of this Riemann sum becomes the double integral. And this is like something you see with the single integrals. It's just applied now for both directions and in the double variable, or the two variable function. Okay, so it's just x, y now, and these deltas are now so small, we call them d. And this is just, okay, remember x times y, this way times this way, that's just the area. So this is our height, this is our area, area times height equals volume. So that's like the simple, more intuitive definition. Kind of uses Riemann sums, not like rigorously or anything. But something we can introduce from this is Fubini's theorem, which just basically tells us from this double integral here, it doesn't matter the order with which you take slices in, right? So here we're saying if I have my surface here, let's say my surface is just a square, right? I can take slices either this way first, so this is our x direction first, or I can take slices in my y direction first. Because at the end of the day, we're going to be going through x then y, or y then x, but it's still just going to be the same volume. The volume isn't going to change depending on which way we go first. So if we integrate from a to b, remember x is existing between a and b values, y is existing between c and d values. Cy, and we're going y first in this case because our CD is on the inside. This will be equal to this one. Right? So just saying does not matter the order of integration. And it's kind of similar to like Claro's partial derivative theorem. Okay. So this is like theorem down, basic understanding of it down. Now the very rigorous definition, or the delta-epsilon definition. So we're saying here, for every epsilon greater than 0, right? So just, we don't know what this means yet, just some random epsilon, which is just a variable, there exists integer n. So there exists some number n such that we want to say the difference between this integral and this approximation to the surface area, or volume, sorry, is less than epsilon. So we're saying there exists some integer n such that the absolute value, because we're just looking at difference here, we don't really care if it's plus or minus, between this integral over some region, right? Some region R, let's call the region R. So this is our thing, this region R of the function minus the double integral or sorry, the double Riemann sum of f that we had earlier is less than epsilon. So there's some epsilon that isn't 0, it's bigger than 0, where we can find some integer n such that the difference between this exact value and the approximation is less than epsilon, right? So we're saying this for all, by the way, all m n in this region. So like we can't take some like random point out here, it has to be inside R, and or not m and n, sorry, x and y, and m n less than n. So we're basically finding like the point at which this approximation is going to be accurate enough where our epsilon works. So it's saying like if we choose, or if epsilon is like getting to a small number, we want this approximation to be better. This here has to be more accurate, right? And for it to be more accurate, we're finding some m and n big enough that such that we're dividing this into a very thin grid, right? Because it's like if I have this little loop here and I'm dividing it into like quarters, these quarters are really rough, like, or these boxes that are made are really, really rough estimates for what this actual surface looks like, right? Compared to like if I basically just, if I made it very, very small to the point where like you can't even see the boxes anymore, right? So like blah, 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 like this. It's basically the exact same thing at this point. And this is going to be better than this one, right? So yeah, now our m and n, as we said earlier, they approach infinity, never actually hit infinity, because if they did, then infinity is not a number in the first place, and also it would just mean that this is the exact same thing as this, and then our 0, this would just be equal to 0 then, which epsilon cannot be, obviously. So we're also saying if this is true, then f is integrable for all smooth functions. And in this case, f refers to the two-variable function. So this is a two-variable function, basically proof delta-epsilon definition for why or how this can exist, right? So we're saying between the exact value and the estimate, it's accurate enough, then f is integrable. Okay. So we think of it as just expanding from a 1D case of a line to now measuring in both, not just the x direction, right? Because here we have like some f of x value times our delta x. This just gives us area. But now we add in the y direction and we add in the y variable. This gives us volume. Okay, so that's basically all 15.1.